GM fellow hackers, I'm Merkeplant, one of the engineers from Chronicle, and in this video we're going to check out how you can integrate our oracles into your protocol. This will be a hands-on presentation, so we're actually going to develop a small smart contract that reads from multiple oracles, and we'll deploy this to a testnet and see whether everything works out. I very much hope so. If this sounds good, then cool, let's start.
And figure out how you can integrate Chronicle oracles into your protocol. For that, first we go to docs.chroniclelabs.org, and yeah, you see here is our Chronicle protocol docs, cost efficient, verifiable data. You know what we're doing. Let's dive directly into the documentation. You see it's still a little bit empty. Everything work in progress. We are working hard to fill this up with a lot more useful information, but here already some information from hackathons that we're going to use now to show how you can integrate and use our oracles. One pre-up just about our new oracle version, Scribe. Scribe is our new oracle version. It is 60% cheaper compared to our previous version and also compared to the competitors on the market, and even 80%, like it has 80% savings compared to Chainlink. So updating the oracle is 80% cheaper in our case than in Chainlink's case. On the long run, well, this has to mean something. Scribe is in that way quite interesting if you are like really into the technicalities, in that it uses Schnorr multi-signatures. We are the first one who were able to use Schnorr signatures on the EVM in a gas efficient enough way. And multi-signatures enable one interesting feature that other Oracle providers still have to figure out because it gives you a moral hazard. And that is if we go to Chronicle protocol/Scribe, so to the documentation, and check out the document to the repository and check out the documentation and go to benchmarks, then we see here two different graphs. One of them looks linear or is linear, and the other one looks constant and is nearly constant. And I just want to quickly get into this moral hazard that you have as a normal Oracle provider, and that is generally the more signatures you have, the more people are signing a piece of data, the more secure it is. There are, of course, like it's not as simple as that. Like if you yourself sign the data 5 times, it does not make it more secure. But if different people, different entities in the network sign the data, the more the better, the more secure. The problem is, however, the more signatures you have, it also costs a lot more to do this signature verification on chain. It's basically a linear increase because you have to add each signature to the call data, to the transaction, and each signature needs to be verified on chain. It's basically a simple for loop for every signature, verify signature. And this means that Oracle providers are generally not actually incentivized to increase their security because it means they also increase with that the cost for updating the Oracle. So there are basically two different ways in how Oracle providers can do this. Either they don't increase their security and run with like a number of signatures, like 7 signatures, which is really not that much, or they have the great idea of moving the Oracle update to the user and basically that you pay for that by having the Oracle update inside of your transaction. Both of them are not really the end solution because in both of them, the protocol is not really incentivized to increase their security with reasonable gas costs. And Scribe is the first Oracle which managed to get rid of this moral hazard. As you can see here, we can increase our signatures to 100 signatures, which is far more than any Oracle provider can currently dream of. And we increase our costs compared to 5 signatures by 2K of gas. So this means it's constant, practically it's constant. And we get rid of the moral hazard of, do we want to increase the security or do we want to pay less to update the Oracle? We can always increase the security. We pay the same to update the Oracle. So this is something really interesting for, if you're technical enough, if you're into cryptography or into EVM low-level programming, this is something interesting for you. But that's not why we're here. Sorry, got a little bit nerd sniped. We're going now back into how you can use our oracles. So let's go into first the interface. Which kind of interface do you need to read? What is the interface? What is the function to read the oracle? And all of this, the iChronicle interface, is defined in the so-called Chronicle Standard repository. This is a repository that we use in nearly every project, and it defines the iChronicle interface. And if we go into it, we see the iChronicle interface is pretty short. This is on purpose. It's special made so that it's very hard to misuse and that it's as easy as possible to use. And yeah, you will probably only need these two functions most of the time, generally always. The read function, it returns to the current value of the oracle, or the read with age function, it returns to the current value and the age of this value. So if you, for example, say you only use a value that's, at most this minutes old or hours old, you can add this check inside of your protocol and use the read with age function to receive the timestamp of the values. Which contract are we going to use now? So we are deployed on a lot of different networks, test networks and production networks. I think the documentation currently has Sepolia and ZK EVM. Okay, let's go with Sepolia, because this is, I guess, the most used test network. And to be honest, I already set up a wallet for that now. So if we see here for the Sepolia network, we see all the oracles that we have here. We have, all the usual ones, maybe some unusual ones like SDAI and DAI, which is quite interesting. SDAI is this DAI version that accrues interest continuously. So here you can basically compute how much interest did SDAI since its inception accrue already an interest compared to DAI. And we also have, for example, EBTA, which is an ETF, like US Treasury bonds ETF from BlackRock. So also a little bit of real-world asset data to play around for you. And of course, all the usual ones, ETH USD, ARP USD, BTC USD. Okay, now we know how we can read the Oracle interface. Now there's one more thing that we need to talk about, and this is the kissing. Let's have this kind of talk. So generally, Oracle providers always have some kind of whitelisting mechanism in front of the oracles, because someone who uses the oracle sooner or later needs to pay. Oracle provider is a normal business, a normal business that has real expenses. We need to update the oracle continuously. This costs a lot of gas. So there needs to be some kind of whitelisting mechanism. And in our case, the whitelisting mechanism is called toll. So we expect a toll. But because we are so focused on our customer relationship, we termed this action of adding you to the whitelist a kiss. So as soon as you become our customer, the first thing we do is give you a kiss. And if you decide not to be our customer anymore, we diss you. This means we remove you from the whitelist. These are the small jokes the engineers like to build into the contracts. Anyway, on mainnet, of course, only we can kiss you, only we can add and remove people from the whitelist on every production network. On testnets, you can do this yourself, just so that you can, for what we are doing now, integrate us and play around with our oracles as much as possible. And for this, we're going to check out the self-kisser repo. And the self-kisser is a really simple contract which just allows you to kiss yourself on every contract on the chain. And we see already there's some documentation about management. And here we can see that we can self-kiss an address via running this lines of code here. And so let's do this. So first of all, I already git cloned the self-kisser repository, and I created another repository called Oracle Reader. This is just a simple contract which has a storage variable, one oracle, Chronicle Oracle. Here we have the interface, the iChronicle interface that I just copied from the Chronicle Standards repository. And it has a simple read function, so we basically just read the oracle one time. And you can call the function, the oracle gets read, and returns the value and the age. Here's a small script included to deploy the contract. This oracle that we're going to read, I just randomly choose now ETHUSD. So this is the ETHUSD address that I received from this list here. We can also use a different one. And we are going to deploy it via this lines of code here. For that, of course, we need to have some kind of wallet. So let's check out how can we create a wallet. Generally, I would heavily put to your heart to check out Foundry. It's a blazing fast, portable, and modular toolkit for Ethereum application development written in Rust. Man, that really breaks the tongue. But okay, if you're on a Linux, Unix machine, you can just run this line of code here. It will install you Foundry. If you're on a Windows machine, just head to the book, into the installation, and here you find all necessary information. There's also a really supportive Telegram group where you can ask further questions if the documentation does not help you enough. And yeah, I would heavily check it out. It's worth it. Foundry is a very good tool, and it gives you, one of the many tools that it gives you is Cast, and Cast itself is a kind of Swiss Army knife for everything Ethereum and EVM related. And why I'm showing to you now is because we're going to create a new wallet. So we're going with Cast, wallet, and then new, and we see, okay, cool, we created a new private key. This is the associated address. So if you now got this address, you can start playing around for the purpose of this tutorial. One thing you'll need is you need to have Ethereum on the network on Sepolia. For this, you need to go to some faucet. I have linked here Infura and Sepolia faucet. So if you have an Infura or Alchemy account, you can get here like 0.5 ETH every 24 hours to play around with. Another thing that we also need is an RPC node. For RPC nodes, generally you can check out chainlist.org, and you can search here for the chain, in this case Sepolia, and you see here a lot of different RPC nodes provided that are for free. Okay, so now we got a contract that we can use to test our oracles. I set up a wallet already with a private key and an address, and I already got some ETH. And I already got some ETH on that address, so we can start playing around now. And yeah, first thing we do is maybe deploy this contract. So via deploying this contract, we should be able to read the oracle. So we need to have some kind of RPC URL. Let's see whether we find a nice RPC URL in the chainlist.org here. Let's take this one. Why not? Okay, and then we need to have a private key. Then we need to have our private key. And let's run it. And we will deploy a contract at this address. Send the transaction. It's waiting now for the recipe so that the transaction is actually finalized. Wait. The transaction was finalized, so the contract creation seems to have worked out. If we go here, Etherscan is not yet updated. I think Etherscan took a moment. Okay, everything worked out. So we created a new contract. It's at this address. 52. This is also the address was printed here. 5288C. 5288C. So this is our small little Oracle reader, which will read from the ETHUSD Chronicle Oracle via this function call. Now we got a small problem because this contract is not yet allowed to read from our oracle. We need to kiss the oracle before. So we go into the self-kisser repository, docs, management. And here we see how we can, for every function that the self-kisser contract has, we get documentation how we can call it. Generally, we need to have one .env file, so an .environment variable file. This is just to give in all our environment variables. So we need to have an RPC node. Let's copy this RPC node here. We need to have our private key. We need to define the self-kisser instance. So where is it actually deployed? Good question, actually. It's deployed at this address. So we can go here. Perfect. Then we want to self-kiss ourselves. So which oracle do we want to be kissed on? The oracle that we wanted to be kissed on was the ETHUSD oracle. So this one. And who should be kissed on that oracle? So who should have access to this oracle? This was the contract that we just created. So this one. Okay, so this should work out. If we now copy this command, run swiss.environment, we are in a different repository, so we have to go into the self-kisser. You see, okay, we self-kissed on that oracle this address. It's waiting for the recipe, sent the transaction already. And it's sent. Okay. And it's done. Cool. So now we should be able to see this on the self-kisser here. We get Chainlink seems to be, Etherscan seems to be a bit slow here from time to time. Now we got it. So we see here we got two events, toll granted. This is from the Chronicle Oracle itself, which says, cool, this address here now has access to the Oracle. And this event, basically, a similar event was also emitted by the self-kisser contract here again. And that's it. Now we are able to read from the contract, from this Oracle reader contract. And let's try to do this by just changing this one function here to something that we just say, okay, we're going to read the Oracle. So we say we got an Oracle reader, which is our reader, and the reader is lives at some specific address, and the address was this one here. Yeah. This. And now we can just say, okay, let's instantiate the reader, the Oracle reader. This is the address. We instantiate it as an Oracle reader. We call the read function. The read function should return us some value and some age. And if we run this now, we get back to the Oracle reader. We have to run again this long script with the RPC URL. In this case, this one. Of course, we had a typo. Otherwise it wouldn't be fun, right? And we see, okay, we got here a value and an age. As you may see, Ether is definitely not worth that many US dollar. That would be a day at which I would not work anymore for sure. So what is wrong here? How can this be? The thing is that all our oracles provide the data in 18 decimals. So we have to basically get rid of 18 decimals here. We can do this manually, 1, 2, 3, 4, 5, 6, 7, but that's a little bit too error prone. We can also use cast while doing it. So if we check here, we see we have here different functions to do type conversion. So in this case, we need the from y function because y, like Ether uses 18 decimals, Ether is in 18 decimals with y. So we have the same thing. So we copy this value here and say cast from y this part. Then we see, okay, ETH is worth 1,570. And this is not off to this what's here currently. So yeah, the oracle is $35 off at the moment. This is also just a staging oracle. We don't update them that often, but it seems to work all out. Nice. So yeah, the oracle, the contract that we deployed is able to read our oracle. The value itself seems to be correct. We also got a timestamp. We know how old the value is. And all of this, yeah, I hope that was not too complicated. I hope you figured out. If you have more questions regarding, for example, Scribe, we got here like ETH Magician post, the Scribe docs, a long Twitter thread in which we go into more detail for other things. Here is more documentation and more information about this. And if you got any questions, please join our Discord. Hit me up. I'm Merkle. Just write something in the Discord. We are here to help, and we wish you all a lot of success and luck integrating our oracles.